Dear audience, let's continue our conference. And in the second session, you will hear 7 presentations of current, former students and teammates of Andrejs' lab. And the first speaker is standing in front of you. It's me, Guntars, and I'm doing quite some experiments in magnetic submaterials. And today I will tell the story, which is basically a big part of my PhD and continues up to now, about the experimental investigation on one of the topics that we have done, and this is magnetic micro-convection. So what is it? What's magnetic micro-convection? It's a phenomenon that was found by Cēbers and Macroscopic in 1983. At least the paper came out, and it's a system where you have between 2 glass plates in a helical cell miscible and miscible magnetic and non-magnetic fluids. So basically 2 fluids that are put together, and if you apply a homogeneous magnetic field, then it starts mixing. And you see this particular pattern, which is quite interesting, and there are several interesting characteristics of this phenomenon. And one of them is that there is a critical field value. A parameter that explains this is magnetic Rayleigh number, and here you can see what are the elements inside, but basically it's the competition between magnetic energy and diffusion. And the thing that you have to remember if you're new to this field, that basically magnetic field is directly related to magnetization, as we are in low field regime. So how did it start for me? What happened was that in 2010 I started working on my bachelor thesis. This was not the topic, but it was happening in the lab at the same time by Kaspas. And it was a simple experiment, basically the same stuff that was happening in the 80s, trying to realize it once again because we had some nice equipment in the lab. But the idea was simple. You use 2 glass slides and put the liquid slowly inside and try to control it basically with fingertips and syringe, and try to bring the fluids inside. So in a microscope you observe only this small portion of the cell, and you see that here in the center, I'll play the video. What you see is the 2 fluids meet, and under the field, which is created by the coil, create this interesting instability. Very nice, a lot of things to study. And one of the things that we're in particular interested was try to characterize these flows around. And for that, a new method called particle image velocimetry was acquired, which basically is adding a bunch of small particles, tracer particles, inside these fluids, and then imaging it with a high-speed camera so that you can catch the displacements between 2 images. Basically the particle displacements between 2 images to characterize these displacements, which basically give you information on the velocities, as you know, the time difference between the 2 images. And to actually make this, there was a bit of a challenge because in the dark region you don't see much of information, but together with the colleagues from the company Dante Dynamics, which is the producer of this equipment, some solutions were found. And this brought to nice results. And at that time, it was possible to compare it with some numerical simulation results, which were a Darcy model. At that time, as you can see, the characteristics are not really the same. However, there is an instability. It has some properties. It develops over time. And these results we could try to compare. There were quite some differences, but at least qualitatively we could explain this phenomenon. That was back in 2013. As you saw in the previous video, the interface formation was really bad. And that's something for me as an experimental physicist is painful. I wanted to improve it. So what did we do? Instead of using fingertips and syringes, we decided to make special connectors and add microfluidics pump with tubing so that we could control this interface formation much better. You can here see the practical example of how it looked like. We had these 2 types of containers from paraffin, which are a spacer between the glass slides, and then slowly injecting one of the fluids, you can get to the point where in the center you image a zone where the interface is formed. And here is a video. How did we achieve it? It seemed quite nice. We could see that the interface is formed nicely. We could do better experiments. Doing better experiments allowed us to characterize it with better care. We did it for various field strengths, seeing the dynamics over time, so we could say much more about the phenomenon itself. At the same time, we learned a bit of using image processing, so we could get the information on velocities on these phenomena, and at the same time, yeah, you can see here it's the velocities over time. For the experimental data, it's the green curves, and there are two models. At that time, theoreticians had added the Brinkman term in the model, and it provided much better results. As you can see, they fit quite nicely. The same if you look at the maximum velocity, and this resulted in a pretty nice paper in 2015. And the best example is if you look at the videos. Here is the simulation of the Brinkman model compared to experiment and Darcy, which was before. You can see very nicely that it looks much more similar than before. So that's quite nice. However, we had one difficulty, and that was called the case of the diffusion. So in the microscopy measurements, when we did them, we could basically, instead of having this micro-convection effect, you could see how this interface, how the magnetic particles diffuse in this water part. As there are no particles, there is basically diffusion happening if there is no field present. And so you can observe it over time. You can characterize this interface, the dynamics over time. You can see that it looks a bit weird, as you should expect some Earth function, but however, maybe there are some problem with the sensor or something. But you can see that at least the characteristic length is growing in time as a function of square root of t, or if you make it squared, it's linear. Hence, it seems like a diffusion process. So if it's a diffusion process, you can say you can find some diffusion constant, diffusion coefficient constant. And the same order of magnitude you could find if you estimate a critical field, which is expected by theory at the same conditions. However, if you look at this same magnetic fluid, you would expect a different diffusion coefficient. You can measure it by different methods. You can actually see the particles by microscopy, and you can calculate from Stokes-Einstein relation the other diffusion coefficient, and you can see that it's 2 orders of magnitude difference. So sort of a small mistake, however, the graphs and videos seem very, very similar. So with this in mind, it was a bit upsetting, but however, you have to move on. And at that time, I sort of started to bring in microfluidics things in our lab, because I had learned something about that in my master's. And therefore, we wanted to put this experiment in microfluidics because it gives even better control. So, of course, in the States, it's much more developed, also in many microelectronics institutions. But for that, you need lithography, ovens, plasma chambers, etc., something that we don't have typically in our lab, and at that time, in basically none of the institutes around. So instead, we started creating microfluidics chips, la MMML, which was basically the same idea, use parafilm spacer, but cut microfluidics channels in them. A cheap solution costs you less than €1, but you get microfluidics chips, and actually was not micrometer resolution, but millimeter resolution, which is perfectly enough for our applications. So that's what we started to do. And if you combine magnetic micro-convection and microfluidics, you get an active mixer. So you can imagine it being used to mix some drugs inside this water part, and which is full of some cells, and therefore it's interesting to apply it in this way. You can characterize how by the amount of field you apply, you increase its mixing amount, and this we summarize in another paper. But one more thing is possible with microfluidics. You can start moving this microfluidic cell around. You can actually turn it aside. And that's something we started, I tried at I think 1 or 2 months before my thesis defense. And then what I found was that actually, if you observe this microfluidic system from the top, you see this anomalous diffusion. If you turn it sideways and put the magnetic fluid on the lower part, it's no more present. And if you turn it the other way around, you see that there's an instability forming because of the density difference. So what you understand is actually that the gravity has been screwing you all over. And this is even more difficult to admit because it was something that was predicted by Andrejs in the first paper we did, but it was only thought to be influencing the very first moment, not the whole process at all. So, and using the same simulation results, we could characterize that this is actually indeed the process that's happening. So, yeah, we could finally explain this 2 order of magnitude difference, and I was happy to defend my thesis with this moment in Paris with both of my supervisors, Andrejs and Regine. However, that's not the end of the story. I'm still continuing it. One part was done by Adela in her bachelor thesis. You can basically start to play around in this system. So if you apply field, you can actually image very closely these nice patterns. As the flow is mixing it together, it's a nice mixer. You can actually in real time see how it performs. And you can start to characterize these properties. And what you see here is the critical field dependence on the flow rate. And you can see 2 things. First of all, you can see that it increases over time. Hence, this flow is the one that stabilizes. This instability, hence you need to apply more field to initiate it. The other thing is that you see that the gravity stabilizes the instability because the field that you need to apply in these conditions is much greater. Hence, 2 more things to work on. So basically, that's something I'm working on, and at the moment it's part of my postdoc project, which is to measure the flows and go back to this stuff that we did at least 4 or 5 years ago, but with much greater precision, as microfluidics allows us that. And that's something that theoreticians have done already. Andrejs Petričenko in his simulations has done a very nice job in measuring calculating the flows that you are expecting around these mushrooms, and that's something I want to see in detail in my experiments in the next few years. So to conclude, there are 3 points I want you to remember. First of all, spend time on improving the experiment. It's worth it. It allows you to see more and find more. Microfluidics can be quite easy. It's not always demanding on things, and never forget about gravity. So with that, I would like to thank you and ready to get some questions if you have. Thank you. Any questions? If not, I will not ask myself a question. I will let Aya. Yes, please.
You mentioned the tree how you bring 2 fluids together.
Yeah.
Just to show one more time, what was the bar separating the fluids, or what?
Sorry?
Here at the beginning of your talk,
yeah.
When you bring two drops together, what was it, a bar separating them?
No, it's actually just the edge of the drop. And it's microscopic, hence it looks dark because it's bending the light rays. That's it. And as it's the thickness of the depth of field is not that great. We see some part of the fluid, so we can focus well in this section. Any other questions? If not, then let's continue with the next speaker. Oh yeah. The next speaker is Sandris Lācis, who will tell about magnets, iron, and rheology.
Good evening, everybody. As usual, if you see some promising title during conference, actually presentation itself is just part of whole topic. So don't be surprised if I'm not telling everything about magnets, everything about iron, and everything about rheology. My first magnetic problem was year 1983, so I'm 35 years in World of Magnets, and it was actually interdisciplinary topic, but my part was to make calculations of magnetic field for elastic magnet. Here is the one. It is drawn here. After it was intention to put that magnet on artery or bypass of artery and somehow influence flow of blood. Actually, it is something like rheology too. Problem was formulated by Andrejs Cēbers, who is not present here but was in the first part. And that medicine part, it was actual for Mr. Kitenbergs, but I don't know what was the outcome of all that medical part of research. I was, when I started the problem, I was a student of second year, and when I was in third year, this publication was published in some volume of publications of chair of our faculty. To characterize that task, I could tell that it was three-dimensional, okay, nice, but number of nodes was just 20 to 24 to 20, not too much. It was needed 10, not 10, but 100 kilobytes, huge amount of memory at that time from computer. We have used some copy of, I guess, some IBM computers called United Series Model 1022. But what was interesting for me, I have first time met plotter. Some plotter board, I don't know, was it made in maybe Germany, but there were no spare parts, and just a pen was put as a plotting unit, which was drawing something, and actually that device was working quite badly, but still I have succeeded to make some computer-made picture, because to draw that picture by hand, it was not at all funny. It was year 1983, and after there was some period when I have studied also things connected with magnets, but I guess I don't remember exactly, was it year 1991 or beginning of year 1992 when Professor Cēbers asked me am I open for new subject, am I ready to go to Paris to study different subject, and I have decided that, well, maybe it will be not huge money, that grant for PhD studies, but at the end I will sure have doctoral degree, except if I'm not at all made for science. And that story ended with defended doctoral thesis work at 15th February 1996. I'm stressing just two family names here from 5 members of jury, because, well, Mr. Jānis, you can see here, sitting, Professor Cēbers and Professor Bakri were thesis directors, they were supervising thesis work. And I'm stressing two remaining persons first, because what is interesting, I should remember that at that time, Professor Cēbers told me that Raymond Goldstein is very promising, at that time still young scientist. Actually, if I look at the birth date, he's just 50 days older than me. And after that time, he has succeeded quite a lot. That information was found by Google today. It is interesting to note that he has won also that Nobel Prize, but for very serious publication, as usually it happens in the field of physics. Then somebody is doing very sophisticated research, but putting nice title. And due to that title, that person is winning that IG Nobel Prize. I hope someday one of my members of the jury will win also real Nobel Prize too. Other person is Prof. Lācis, nowadays retired but still trying to do some science, if I understand correctly. After thesis work, I had a feeling that I'm slowing down and I should try something new for people from Soviet Union. I should try to find some postdoc position. By help of Andrejs Cēbers, I have landed in Nice, where that group of Lācis were working. Well, probably that science was not doing so interesting science for me, but somehow I did some small things and well, after I get some common publications too. But the real subject about small science will be what I'm doing during the last 2 months. Actually, if you think that it is gas here in our kitchen, it's not really that. That is a small disk magnet. And problem given to me from two young persons from Professor Cēbers' group, Jānis, Cīmurs, Guntars, Kitenbergs, and actually that problem is possible just because in laboratories they are doing very nice measurements of magnetic field. What we have used is quite a large number of measurements on some grid, 81 to 81 to 11. And with Jānis Cīmurs, I guess we have agreed that I will try to do something in that field. It is interesting for me because I'm calculating some integrals for boundary integral method, and it was the impression for me it's very easy. So we have introduced magnetic monopoles. Of course, that is a bit fiction and just mathematical trick. We are putting some surface magnetic charges, and that is a way how to represent magnetic field. Magnet itself, it is not so large, and what I was expecting it will be very, very easy task, but actually it turned out not really like that. Here you can see calculated magnetic field, difference between calculated and measured field, and also surface charge sigma. If you look at that picture, you can maybe see that surface charge is making strange patterns on the surface. That color blue, color red. It is not what I was expecting. And if I'm drawing that difference between calculated and measured field, it turns out to be, in this case, quite chaotic. It's not extremely large, but I should compare with the largest values of measured or calculated field, and I see that in this case it is about 25%. So for some points the difference is quite large. I can do again the same calculation, but not taking into account all points measured, but just closest ones. And then we see again that maybe there is some pattern-like structure, but it still seems to be chaotic. And I can see also that, oh no, yes, I can see that value of difference, it is smaller. It is about 5% in this case. So maybe it's already something what we want, because if I correctly understood that outcome of this small problem is just needed to have good representation in proximity of magnet, not far away, because far away everybody knows that it is dipole behavior. Maybe let's skip that picture, and it's almost the last one, I guess. But what is different here? If I see that physics in what I have calculated, well, it's just mathematical method maybe, but I still want to see some physics inside that. Then we can simplify the models, and we allow just plus and minus layers of magnetic charges, and organize in such a way that the total charge is zero, what really happens because we don't have magnetic monopoles. And in this case, if I took just the smallest part, oh no, I guess I'm lying a bit. No, all points I've taken into account, but I'm showing field difference between calculated and measured one at the proximity, just one layer, and we see that maybe problems are also due to the fact that I have impressions that magnet should be shifted to get correct position according to what was measured. So, what to do next is maybe take that last approach and add something like another kind of charge distribution, higher powers according to that expression. Oh, no, here. I can take different powers. They are like different members of polynomial, but they have zero charge at the surface. But I have not done that yet, but still I want to show that some ideas we have. So, what is the conclusion? Conclusion is that in some cases even very simple tasks turn out to be a bit intrinsic. And what I have not mentioned is that, the idea which was thought to be a good one at the very beginning, that I will have many degrees of freedom. The degree of freedom will be surface charge value of nodes at nodes, and between nodes there is linear interpolation. Actually, that approach gradually leads to system of algebraic equation which is not solvable correctly for larger number of nodes. It's reaching numbers, even small one number, 1000 leads to that matrix which provides artifact and not solution itself. Okay, that's all what I wanted to talk, and thank you for your attention.
We have some time for questions. Yes, there is one question, please, Professor.
It's important on the perimeter of this because there is singularity of the field. It is infinite, actually. Or you don't see?
Well, that singularity, of course, should be mathematical, because we know that all atoms have a finite size. So if we go to atom size, there is no singularities. I don't know what happens at that size, of course, but what I would expect if that first approach would work, when I have plenty of nodes and triangles and linear distribution of surface charge, I would expect that the solution itself will show what is going on. Maybe a smaller amount of charge at the corners. I don't know, but we are not calculating field at the corners. We are just assuming there is some distribution of charge, and we are calculating field at the distance from those nodes on the corners. So we don't meet that singularity. So I hope.
So thank you. I guess the only thing is to comment that this is Andrejs Cēbers' footprint in the main aula of University of Latvia from today's ceremony in the morning. Yeah, with the balloons. The other 5 are there, so But with this, we thank Sandris, and thank you again. And the next speaker is Rūdolfs, who will tell us about the mathematical modeling of filaments, about current practice and future.
Good evening. My talk has a bit of a dual purpose. On one hand, as befits a talk containing the phrase mathematical modeling in the title, I do want to give at least a cursory overview of the mathematical framework we use to describe magnetic filaments. But on the other hand, I want to use this background to make a bit of a more general point about the development of computational soft matter, at least as it's relevant to flexible magnetic objects of different kinds, not just filaments. The advent of the modern interest in magnetic filaments, I think, began in 2003, when the first paper describing a practical experiment where a superparamagnetic filament was used effectively as a sensor to describe the elastic properties of the linkers used to bind the superparamagnetic particles together was published, and in this experiment it was found that these filaments form characteristic metastable hairpin shapes. The same year, this was described by Professor Cēbers in my view, a very important publication which described the first mathematical model that could predict the evolution of these shapes numerically. This was done in the so-called tangent-angle formalism, which was intrinsic. I'll describe what that means shortly. And finally, in 2005, a very famous experiment was published in the journal Nature by Dreyfus and collaborators, in which they used a superparamagnetic filament to carry out controlled transport of erythrocytes, red blood cells, in a direction of their choosing, as shown in this video. This naturally attracted a great deal of attention and drove also the development and proposal of many other prospective applications for flexible magnetic filaments in different field configurations, and not just superparamagnetic but also ferromagnetic filaments as well. These filaments are slender, therefore it is a natural choice to describe them as analytic curves, describing them essentially by their geometric center lines, and using the standard framework of differential geometry for that purpose. This naturally leads to the so-called Frenet frame, where the filament is completely characterized by its tangent, normal, and binormal vectors, and the Frenet equations that describe their relation to the curvature and torsion. These are the intrinsic properties of the filament. And then, if the filaments can also twist, then there is a further complication. We have to take into account the fact that in the real world they're not infinitely thin. And so, in order to do that, we introduce the so-called material frame, which can be related using the double vector, effectively the manifestation of the rotation operator operating on these basis vectors. We can relate that to the curvature and torsion and the so-called twist angle psi that I've tried to illustrate here, that simply describes the deviation from this newly introduced material basis vector from the Frenet normal vector, which is caused by the fact that the filament is of finite thickness after all. And in addition to all of this, we typically impose the condition of inextensibility, which simply states that the filament conserves its total length. Now, if we accept this framework of kinematics, then we can express the total energy of the filament in a fairly standard way. It's composed of the bending energy, the twist energy, the magnetic interaction energy, and also this internal tension term that serves to ensure the extensibility of the filament. It may be seen depending on a particular application, as either the manifestation of a physical internal tension or simply a Lagrange multiplier approach to conserving the length of the filament. Then depending on the material of the filament, whether it is superparamagnetic or ferromagnetic, you have different types of different terms for the interaction energy with the external magnetic field. And then using standard techniques of variational calculus, we can derive expressions for the forces that act on the filament. Now, if we were only interested in describing the shapes of filaments in a vacuum, this would be all we need. Unfortunately, typically we're interested in filaments in fluids, so in order to obtain equations of motion, we also need some hydrodynamics. The most primitive approach to this, and the one by far the most widely used in the literature, is the so-called resistive force theory approach. Now, all of this relies on the idea that the filaments are very small, they move comparatively slowly, and so we are entirely in the Stokes regime. Reynolds numbers are very small, and in that regime, because flows are stationary, it can be shown that the entirety of the complexity of this hydrodynamics can be condensed into a single mobility tensor, or equivalently its inverse, the resistance or friction tensor, which can be approximated by a variety of methods. Now, the simplest of these is simply to assume that the friction coefficients in the tangential and normal directions are different. Their ratio is some sort of a constant. In an extremely simplified case, we can derive that constant analytically. For a slender ellipsoid, it tends to the value equal to 2. For real filaments, it turns out to be somewhere in the range between 1.5 and 2. And this has been the approach almost universally adopted over the last 15 years to describe these filaments. Unfortunately, as it is a very simple approximation, it is not always sufficient to capture even the qualitative nature of how the filament behaves. And to that end, we've also tried more sophisticated approaches to hydrodynamic interactions. Now, the next simplest approach that's possible is the so-called Rotnik-Krāvī-Janov-Hubbard tensor. This effectively takes into account all the possible two-particle interactions in the Stokes regime. And unlike the resistive force theory, which assumes that the filament is asymptotically thin, the RPY approach simply models some discrete ensemble of spheres. It doesn't matter if they compose a filament or some other structure. There are also higher order approaches that are possible and that we have tried, including multiple expansions, which can theoretically be asymptotically precise as long as you have enough computational power. And of course, if all else fails, you can simply resort to solving the full complexity of the Stokes or the Navier-Stokes equations. The question naturally arises, how much of this tremendous complexity do we actually need? People have typically stuck to using resistive force theory because it's very simple and because it's very computationally efficient. For a ferromagnetic filament in a linearly oscillating magnetic field, it turns out that the motion is supposed to be entirely periodic. The fact that it struggles a bit is a function of the computer, unfortunately. But it will continue in this stable swimming motion forever in the resistive force theory approximation. This regime is perfectly stable. On the other hand, if we do the exact same thing with exactly the same parameters and vary only the degree to which we approximate the hydrodynamic interactions, this is the next simplest approximation, we see very quickly that the filament relaxes into a different metastable state, an S-like shape, which is no longer useful for control of propulsion in a specific direction. This is a qualitative difference, and this is something we found very quickly when moving to more accurate descriptions of hydrodynamics. There are other examples, and the question naturally becomes, is this enough then? Is the RPY approximation enough, or do we still need more? before I get to that, it's worth noting that the complexity has a price, and the price is very steep. The simulations that I just showed, the simplest one, the resistive force theory approximation, takes something on the order of half an hour or an hour on a modern desktop computer to calculate. That's perfectly fine, it's cheap. If you do a naive implementation in a high-level language of the Rotnik-Kroger approximation, that costs you 2 orders of magnitude more in computation time. I have shown, and people in polymer physics have shown in different applications, that if you do the Rotnik-Kroger approximation efficiently, it's possible to get that cost down to something fairly negligible, about 20–30%. So my contention number 1 in this talk would be that the RPY approximation should be the reasonable minimal default. That using the resistive force approximation is simply not justified anymore. However, if we go beyond that, if we go to multiple expansions, that cost becomes extremely steep indeed. For instance, this simulation that I mentioned, if it takes half an hour on a desktop computer, doing the equivalent thing with the multiple expansions would take you a bit over a year. That's fairly expensive, and that's a very simple system. We want to model bigger things, we want ensembles of filaments and so on. So clearly some compromises have to be made. But on the other hand, if doing the multiple expansions is so expensive, why not go the whole way and solve the Stokes or even the Navier-Stokes equations directly? Could that perhaps be more advantageous? To that end, and this is something I've been working on more recently, the fact of the matter is that on modern computing platforms, the key to efficiency is your ability to parallelize computation. That means minimizing dependencies in computation. The problem with multiple expansions is that there's only so far you can go in parallelizing them. They rely very heavily on a number of sequential data dependencies. By contrast, there are approaches in modern computational fluid dynamics that can be implemented far more efficiently in modern computers. Then again, conventional CFD solvers also have a number of problems when applied to situations such as these. The first of these is the need to regenerate your entire mesh if it changes substantially between each time step. That's an extremely severe efficiency limitation that can be circumvented by using so-called immersed boundary methods that were invented by Charles Peskin in 1972 with the purpose of modeling blood flow in the human heart. That particular method transfers the burden of enforcing boundary conditions to effectively an external force in the Navier-Stokes equations, which is calculated by transferring the effects of an entirely separate Lagrangian grid to the fluid grid by a number of operators, the interpolation and spreading operators that I've written here. These methods by now have a fairly well-developed theoretical background and a wide literature, but they only circumvent part of the problem. The other problem is that solving the Navier-Stokes equations is currently bottlenecked by the performance of solvers for the Poisson equation for the pressure. That again is a problem that can only be parallelized to a limited degree, and that's not going to change. The mathematical facts aren't going to change, so we have to adapt to the hardware we have. One way to doing this is by using the so-called Lattice-Boltzmann method, which is far more parallelizable because by virtue of its mesoscopic approach, it consists of two steps, the first of which is perfectly parallelizable, in the sense that everything that's going on is only local to one grid point on your computational grid. The other step, streaming, or advection, equivalently, is a nearest neighbor interaction. So you only care about the neighboring breakpoints. That's a very efficient solution. And these two approaches that I've described, the boundary methods and Lattice-Boltzmann methods, have been recently combined to yield highly efficient solvers, at least in the regime of fairly small to medium Reynolds numbers. That's about the range between a fraction of unity and about 100 or so. Within that range, it's been shown not just, and this is my more general point, none of this is restricted to filaments specifically. These are general problems in computational soft matter whenever you have some kind of elastic structures that change rapidly over time. And when you need a high degree of accuracy for the fluid flow around them. In these cases, it's not a magic solution, but it frequently turns out to be the case that on modern computers, particularly utilizing things like GPUs and ASIC accelerators and so on, that these Lattice-Boltzmann boundary methods are in fact very efficient, not just for elastic filaments, but also for various viscoelastic problems, various networks of filaments, various suspensions of particles, and so on. So they have a fairly general applicability. Now, this is a very preliminary demonstration, but this is an example of a rotating filament subject to an external magnetic field. It's deliberately chosen to be in a parameter range where it rotates very slightly, because this is a range where we know what the physics are. This is an extremely simple problem, so we can compare them to other approaches, to other solvers. We can compare accuracy, efficiency, and so on. And the results in that regard so far are very promising. But obviously this is work in progress. With that, I'd like to thank you for your attention. We'll leave you with this rotating swimmer that's going to keep going round and round while you're hopefully asking some questions. Thank you.
Unfortunately, to fit with the time, let's keep the questions for the coffee break afterwards. And thank you, Rūdolfs, again. And now I would like to welcome the next speaker, Jānis Cīmurs, that will tell us about individual magnetic particles in the magnetic field. And let's try to get to your presentation.
Yeah, my work with Andrejs started in some 7 years ago, as I can count. It was in the year 2010. At the beginning, we started with some rheological problems, something magnetical, and then I read the book Strogat's Nonlinear Dynamics and Chaos, and then the real work started, because I understood how to calculate the stability and instabilities of systems, and that's what is main part of my PhD and some afterwards work. So my talk going to be about my research in lab, which is related to the individual magnetic particles or dilute solutions of magnetic particles, and how it's related to my work and work in lab. So why individual particles? To explain some trajectories of magnetic particles, which you probably heard already in this talks, understand energy dissipation, which involves in magnetic particle, which is for magnetic particles very important in some applications in hyperthermia. There was a paper in Nature about Jānis particles, which made very interesting structures in a processing field, so we wanted to explain it, and one of the largest part of my work is developed this part, As you already heard about Crick experiments, so explain some uses of particles in rheological measurements, and probably some use in nuclear magnetic resonance, which also I have touched in my work. And the ending part I'm going to talk what I'm going to do further, and I'm interested in some field configurations, how I can tune the interaction between the particles and make them attract each other or move in different directions. What I started is Stoner-Wolfart model, which has two parts. The first part is magnetic part, where magnetic particle with magnetic moment in the direction E, and it wants to rotate to the direction of external magnetic field. The second part is the part due to the anisotropy of the particle, and the magnetic moment wants to rotate to the direction of the anisotropy of the particle. It's squared means that it doesn't matter if it aligns with the direction of the particle or is opposite to it. So that's why it's squared, and if we plot this energy, it's here in black color, then if the magnetic field, this H is small, and we fix particle in place and rotate magnetic field, then we see that the magnetic moment, which is black, stays near this axis of anisotropy. On the other hand, if magnetic field is large compared to some critical value, then magnetic moment of the particle rotates with the external magnetic field, and it rotates around. If we have something in between, then there is the interesting part that the particle moves with the external field, and at some point there is a drop. It jumps from one energy minimum to another with a jump, and in this jump there is energy dissipation, which heats the particle, and afterwards it heats the surrounding fluid. If we put this particle in a rotating field, the particle with this Stoner-Wolfart model, then there is possible three regimes: synchronous rotation with the magnetic field, precession in this field when the magnetic particle goes out of the plane where it rotates the external magnetic field, and the third situation is this asynchronous motion, asynchronous rotation of the magnetic of the particle. And if we calculate the stability and we make stability analysis of this particle, then we find that if the rotation frequency is low and the magnetic field is high enough, then the particle rotates with external field. So large field, low frequency, synchronous rotation. On the other hand, if the magnetic field is small and the frequency is large, particle likes to go out of the plane where the magnetic field rotates, and it starts to precess around the axis of rotation. If the both magnetic field is large and rotation frequency is large, then we have this back and forth motion, or this asynchronous rotation. And in the between, in this region, there is possible both of these regimes, and which of them gonna which of them is going to be stable or we're going to have, it depends on the starting conditions we choose. We can have one or other of these two situations. That's one part of my research. The next part is using superparamagnetic particles, or just simple paramagnetic. These are the particles where magnetic moment is induced by external magnetic field. But if the particle is not round but spherical, spheroidal, then the magnetic field will try to align with the longest axis of the particle. So the particle can be prolate or elongated, or it can be flattened or oblate, and then all the directions around there is equal. And if we put this particle in the pressing magnetic field, it's a magnetic field that rotates around, but it's have some direction, constant direction in the direction where it rotates around. It's shown here, and there is some angle which magnetic field has with rotational axis. If we put it in that field, there is possible two regimes: synchronous rotation or asynchronous rotation. And in dependence on the angle we have and on the frequency of the external field, there's possible that if the angle is quite small, or that says that the particle is, or the field is more vertical than horizontal, then this elongated particle or a prolate spheroid will rotate synchronously. In the other situation, if rotation frequency is large and the field rotates close to the circular, then we have this asynchronous rotation, where the particle rotates and at some point falls back and makes back and forth motion, and with that it makes also a wobbling. It's like it's one end up, and at the other point, the other end of the particle is up. The same calculation, the same equation is also answered the question for the oblate particle or the flattened particle. And it shows that in this situation where the field frequency is large and the field rotates close to the rotational, then this flattened particle is rotating synchronously. On the other hand, if we take lower angles of the pressing field, then the particle goes this wobbling motion where it flips up and down. In this middle region, we have that both the rod-like particle and the plate-like particles both have synchronous rotations. We have done also experiments with this, and here you can see that there's this wobbling can be seen also in the experiment, and also you can see that probably not that the rotation is not uniform, but it's a bit goes slower and faster. I have worked a bit with rheological measurements with the particle. When it turns the field on, the particle moves in one way, and then when the field is turned off, if fluid is viscoelastic, then the particle moves a bit backwards, and from these trajectories we can calculate the viscoelastic properties of the fluid. I have also worked on stochastic calculations of the particle motion when the particle is in this viscoelastic fluid. I have done numerical simulations and some theoretical calculations, and as you can see, I had some problems to get the theory is exactly the same as numerical. This is not done till the end by now. And also I have done some calculated dissipated heat due to the magnetic moment jumps if we put on the AC field on the particle and calculated this period dissipated energy. What I'm gonna do further in my postdoctoral work, I'll try to check what happens if we take two particles and would they attract or repel from each other. Afterwards, I'll check if we take more than two particles, what happens, what structures they're gonna make. Gonna these structures change if we add some hydrodynamic interactions, add some more interesting magnetical or hydrodynamic features to the particle. That's it. Thanks for the listening and hope to hear some questions. Yes? Go.
Yes, we have time for one question. A quick question. Anyone? Those are not running questions, I guess. Yes, there is one. Please.
Are there experiments yet for a rod in a viscoelastic fluid?
Yeah, we had the same. I think the same that you did. I'm not sure that.
But I mean, in a rotating field, can you get the thing really to?
In viscoelastic, not yet.
There's a very weak elasticity.
We have done only this and
So it's solid and come back. Yeah.
And they're not at all viscoelastic.
Okay, that was a perfect quick question. Let's thank Jānis again. And the next speaker is Oksana Petričenko, and she will tell how is it actually to be a chemist between a bunch of theoretical and experimental physicists. Experimental anesthetics.
Dear colleagues, I want to introduce you.
Yeah.
I represent a chemical unit in the Laboratory of Magnetic Soft Materials. In 2005, was created experimental group in the chair of the theoretical chemics in the physical department, and they wanted experimentally proved and or check some theoreticals some theoretical problems, and for supplying this experimental work was necessary to provide magnetic materials. And anyway, in 2005 was created chemical unit, chemical laboratory, and laterally from the zero. And while the attic space was transformed to the chemical laboratory, Professor Cēbers found me a place where I could did my first synthesis, and this was laboratory of in the Organic Chemistry Institute in the membrane active laboratory. The chemist who works there was interested in these magnetic materials, and since this time, since now, we keep very deeply friendly and good working relationships. So, for this time, I was opportunity to did some voyage to Paris University, Pierre and Marie Curie University, where I can improve my skills and to know more about these magnetic materials. So we start work in our now laboratory in 2008 year, and gratitudely filled with equipment. So this is research interest of the Laboratory of Magnetics of Materials, and my task in this was executed develop biocompatible magnetic materials, create materials with functionalized nanoparticles, and investigation and characterization properties of the produced materials. So first, magnetic colloids. For synthesis, I applied co-precipitation method, which was presented by Massar, and we can obtain nanoparticles, Mahimite nanoparticles with positively surface, Mahimite nanoparticles with coating with negatively charged surfaces. It due to cyclic ions covering, and particles was functionalized by such polymer as dextran and magnetite and mahimite nanoparticles, and we can do some fluorescent nanoparticles. Next, one more nanoparticles example of functionalized nanoparticles is magnetic liposomes. Liposomes is a spherical formation with inclusion in center, which is isolated with bilayer membrane from the surrounded media. If internal this volume is fulfilled by magnetic liquids, we have magnetic liposomes. For the magnetic forming, for liposome forming agent was executed lipid-like compounds, which was synthesized in the. I talked about this laboratory where I do my first synthesis. This is synthesized thing. Why these compounds? They possess these polyfunctional pyridinium amphiphiles possess self-assembling properties, and is interesting for due to contain the one for dihydropyridine ring. This is one. And it is an active linker, which can in intrinsic structural part of many pharmacologically active compounds. And you see, this is as illustration. 3, this and this, liposome dispersions. For preparation, I used 3 I forget. We have, this one is a structure of the, when we have some substituent derivatives. Yeah. In this case, changes was made in the, this nonpolar, in the chains nonpolar. And you see that with elongation of these polar chains, how it influenced to the formation of liposomes from the big sizes to the small sizes. And also this we can see liposomes with one belai, but also exist many liposomes with multi-layer. But with in this case, more liposomes with one belai around that form liposomes. So, for the investigations of these objects, nanoparticles and liposome dispersion, it is list of the applying methods and equipments. And you see, not only I use not only equipments that has in our laboratory, but also in the another institution, and I am very grateful for people who helped me in these investigations. So now we in the chemical unit executed a postdoc project, and actually it is a continuation. This project is continuation for my preliminary work, only with more tasks. For example, I must produce new objects, magnetic objects with different nanoparticles with different shape and sizes, and I wanted to apply not only the precipitation method, but another, maybe electric formation, maybe thermal decomposition, to obtain the hematite, ellipsoids, magnetic filaments, and maybe tablet-like nanoparticles and others. With further investigations of dependence of magnetic liposome formation on the structure of pyridinium amphiphile, because before very detailed was investigated only one derivative. Now I have it 7. So, and it is shortly all about jobs provided in the chemical unit, and I want especially gratitude to Professor Cēbers for his patience, persistence, for involving me to the scientific job, and making me to further for all. Sorry.
Thank you, Oksana. Any questions to Oksana? Or no chemists in the audience? Too many physicists, right? Okay, thanks, Oksana. Let's thank her again. We invite the next speaker, Ivars Driķis, who will tell us about Labyrinths.
Good evening. Long time ago, I was very interested in labyrinths. It was a long time ago, as you see. And I was very interested in especially in labyrinths that are created due to interaction between two kind of forces. Short-range attractive forces and long-range repulsive forces. They include also magnetic fluids, the layers of magnetic fluids. All this kind of labyrinths looks similar and behaves similar. In my case, I was working with magnetic fluid in teleshore cell. External magnetic field was applied. Experimental setups look like this. But I was not working with experiments, I was working with numerical simulations. And, before, why labyrinths arises? Labyrinths arises because due to applied magnetic field, they are introduced, as Sandris says before, fictitious magnetic charge, something like that, and they build dipoles, and dipoles repulses. From other point of view, there is surface. Every surface has tension, so it's repulsive force, attraction force. So, okay, now I will show you next few movies. There was two kind of movies. First kind was labyrinths built from separate droplets surrounding by big magnetic fluid area. So around this there is magnetic fluid to keep these particles inside. There was in some initial conditions. In one case randomly, second times periodic, and there was step-by-step increasing of a magnetic field, and then we see some labyrinth. Other situation is similar to this, something similar to this. But again, I want to make this from separate droplets. So in this case, the periodic system, and again something arises. So movies. I will entertain you with movies. Step by step, and you will see how labyrinths are formed. There was a day that maybe we can send this to some weekly journals to make paths between these lines, but you know, science that is built from separate droplets, always multiple paths exist, and it's not very interesting. So, relax his back. Almost like in the beginning. No? Okay. Another one. There, this droplets initially was regular order. Despite of that, finally we have labyrinth almost like new life. Almost the same. Maybe some of them are slightly.
It is just like a classical Jeffrey Taylor experiment, actually.
Computer experiment. So, another, then, not so. There was slightly faster. All this is done by longer integral equation.
Ivars has been very good PhD student. Each day he has submitted to me some kind of new movie. I guess he was the best.
Seems to be it's all. So when you have enjoyed this computer for a long time, okay. So you have enjoyed this computer, you solve various technical problems with programming computers, how to run your programs for weeks. Yeah, it was quite a long time ago. And finally, a question arises. How to convert this to doctoral thesis? In physics, not in computer science. So, we know answer. We know who write all formulas.
Ivars said he will never write. I said, no.
So, the idea is following. If you have a pattern of lines, there it's possible to write formulas. And the idea was to apply these formulas to our regular patterns. So to get some characteristic size from this. In principle, it's clear how to do. It's a Fourier transform, 2D Fourier transform, and it shows very well correspondence. Of course, in this case, it's big deviation due to the fact that the system is small, and the characteristic size is comparable with the size of system. With lines, the situation is not so easy. First, we can simply check that this hairpins arises, as Cēbers predict, on 80 degrees. And it arises in experiments and arises in the same moment in numerical simulations. To get some undulation threshold, as before, I tried to do 2D Fourier analysis, and when I drew this graph a long time ago, I was almost sure that everything is okay. I still think it's too noisy. Everything is too noisy. Finally, I have such idea. So the task was how to put analysis from 2D space to 1D problem. And I call it periodic mean or some backbone of all this system to eliminate these slices. And when it's done, it's very beautiful Fourier spectrum. We can try to again return back and test whether it works so good or not. So, big thanks to my taste advisor. All pictures.
Who is this man?
And where it is? Just here? Yeah, I just look this week for old photos in my home.
Thank you. But before Ivars runs away, any questions about the labyrinth? You saw a lot, yes?
Kāpēc to animāciju pārtrauc tad, kad sāk strauji kustēties tā bilde? Magnētisko lauku ceļiet, esiet cēluši un tā bilde slinki kustas. Bet tiklīdz kā viņi sāk straujām kustēties, tā liekas, ka kaut kam jānotiek un uz nulli.
Toreiz tas prasīja ļoti lielus datoru rēķināšanas laikus, un viņš kustējās tik strauji, ka jāņem bija ļoti maz laika soļi. Tur nekas tāds, ko Cēbera formulas aprakstīja, vairs nebija. Taupījām mēs laiku toreiz. Mums laiks tagad varētu pareiķināt priekšu varbūt.
Okay, let's thank Ivars again. Now let's wait for Artis, who is giving the last talk of the session about PF1 micro-rheology with optical tweezers. I guess you can find it. Yeah, you can do it.
Good evening, everyone. So my topic will be on low concentration bacteriophage PF1 microrheological measurements with optical tweezers. It's not going to be an overview, but it's going to be sort of a recent study. So about a bacteriophage PF1. So what is a bacteriophage? It's a virus that can infect and it multiplies in a bacterial environment. It's shown in the picture here. It's sort of a cylindrical fiber. It's not very long, it's 2 micrometers long, but it's way more thinner than it looks in the picture. It's 6 to 10 nanometers in diameter. So you can't see it in the microscope. It sort of consists of DNA core, and it's coated in layers with various proteins. The main problem is that it sort of creates a biofilm over different bacterial surfaces, and it sort of covers it. And for example, in human body, it might happen in lungs, and when it covers this bacterial surface, it sort of makes it unreachable for any medicine. That's why it might be interesting to study. So previous experiments we've done with magnetic microrods in an oscillating magnetic field. It's sort of in the field of microrheology. we acquired certain results, but we wanted to sort of prove or disprove this data with a different method. And so this different method, here comes the optical tweezers setup that we want to sort of compare. So the setup looks something like this. Here's a laser in the infrared region. It's 1064 nanometers. It goes through the telescope with a lens ratio of 4:1 to increase the diameter of the beam. And then this beam goes into the microscope and it goes through the objective, and it sort of creates a trap in the sample plane. Then we acquire the interference pattern, and it sort of shows on the quadrant photo detector, and it sort of then is sent to the computer. So here is sort of a picture of the sample plane. Here is the sample. Sample will be characterized later, but well, here is also the piezo table, which we can move in X, Y, and Z direction. So how does the trap work? It sort of consists of, well, theoretically consists of two forces. One is the scattering force and the other is gradient force. The scattering force depends on the coefficient of refraction of medium, of the intensity of the laser, the speed of light, and the sigma, which is sort of cross-section of scattering area with specific radius r, which is the radius of the bead. The gradient force, on the other hand, is also dependent on some of these variables, but it's also dependent on the polarizability of the bead. Well, it sort of looks like that this is the beam shape. It's Gaussian. Well, theoretically it's Gaussian. Of course, in experiment it might be a little bit different, but closely as a Gaussian. And then there's a bead introduced in the sample, and preferably we catch the bead in the trap. And so the scattering force is, if the scattering force is not strong enough to overcome the gradient force, which sort of pulls the bead towards the focus of the light, then we sort of come to an equilibrium, which would be most likely somewhere here, where the scattering force is approximately the same as gradient force backwards to the trap. So, if when we get to the measurements, first we have to calibrate the tweezers. First we make the sample, we let the beads in the sample sort of, due to gravitational effects, to settle down. We wait for a while, these beads sort of stick to the surface, and then we sort of cover we go with the trap over the bead in X and Y direction, and we sort of calibrate the photo detector signal as we, in this case, later can know how far from the center of the bead is the trap, and what is the signal in that case for the detector. We assume that if the bead is trapped in the trap, not stuck to the surface, then the bead would only deviate from the trap a few nanometers, well, or micrometer at most. So we assume that the case when the bead is trapped is this part when it's linear. And when we fit to this data, we sort of acquire the detector's relation to the deviation of the bead from the trap. The other thing we have to calibrate is the trap stiffness when the bead is sort of introduced in well-known medium, for instance in water. We acquire this signal. Well, so we trap the bead, and this is basically the signal that it's giving out. So we fit it with the Lorentz fit, and we acquire the coefficients that we sort of later can, from which we can later calculate the trap stiffness. The trap stiffness is shown here. It's 0.058 piconewtons per nanometer. It's relatively low. In our setup, we can acquire a higher trap stiffness, but the problem was that if the trap stiffness is very high, the bead deviates from the trap very small gap, and the signal is hard to analyze. So we sort of dropped down the stiffness or the power of the trap, and we went with this trap stiffness. The sample that we measured was with concentrations starting from just the water sample up to 0.1% of PF1 concentrations. It's weight to volume, and introduced the beads that we could capture in the trap, and then oscillate at a certain function. These beads are made of streptavidine polystyrene. The radius of the beads is 3.28 micrometers. And their concentration is enough for a few to be within within the angle of the view of microscope, but not too little so we could find one. Then we sort of oscillated the piezo table, on which the sample was stationed with this function, and then we acquired the signal on the photodetector, assuming it would be this function. And in the result, we acquired the phase difference between the sort of oscillation of the sample and the oscillation of the signal. And the results are these, that for a water sample where there is no bacteriophage introduced, we acquired these data, so we can see on the y-axis is the phase difference in the angle, with angle of in degrees. So here are 0 degrees and here are 90 degrees, and on the x-axis we see a frequency. The frequency is at which we oscillated the piezo table. So when the frequency of the piezo table's oscillation increases, we can see that the phase difference between the table's oscillation or the sample's oscillation and the bead's deviations oscillation on the detector sort of increases, which is expected. And for a more viscoelastic media, when we introduce the PF1, the phase difference also increases. We have not yet compared these data to the previous measurements, but that's expected to be done. So, thank you.
Okay, so with the privilege of being the colloquium chair, I ask Artis to push the button and sabotage this question session. Please ask him during the coffee break. But we have small announcement from our laboratory colleagues. We do prefer one tradition we have already for quite many years. Andrejs Cēbers is hosting a barbecue party in his summer house, and we like it so much that we want to give a gift from us to your birthday. It's coming slowly there. In order to continue this tradition, thank you very much for what you have done to us, and we hope that this tradition continues.
Sure.
And now it's the word for other greetings, please. It's against the safety regulations here.
Nu, prieks tev, Andrej, redzēt, mundrus, sautu, runājošu, varošu, un tā godīgi sakot, senos laikos līdz pagājušā gadsimta 90. gadiem bija tāds teiciens, ja nokārto matfiz metodes, tad var precēties un darīt visas citas lietas, jo, kā zināms, diplomu gandrīz jau kārtā, ja? Nu, situācija mainījusies, kad, matfiz metodes ir stiprā mērā iznīdētas, nu, jaunais laikmets, digitāli un t. Nu, viņš tā, diemžēl ir, ka tas ir nodzījis uzcīt pagrīdē jau, bet mums ir laboratorijā tāda laba tradīcija, ka, nu, principā, tos, kas nav izgājuši filtru pie Andreja, vai nevar iziet filtru pie Andreja, tos vai nu darbā neņem vai atlaiž, ja? Jo tu esi... Jā, paldies tev par to. Tāpēc tur ir tāds pozīcijas stipri, ja? Un tāds mazs džentelmeņu komplekts tev. Šķidrums, jā. Bet mēs neriskējam tev nes 70 litrus, ja? Jo tas būtu drusciņ pa daudz to veselās klāt. Lai tev veicās uz priekšu. Paldies tev.
The announcement of Professor, the conference is closed, at least this colloquium. Thank you for your attention.
Thank you.